My initial interest in it was mostly just because we find ourselves in this beautiful but chaotic universe, and I wanted to know what the underlying rules and laws are underlying our universe. And I believe you're in a law school, is that correct?
Correct, yes.
Yeah, well, so physics are the fundamental laws not written by humans, so it's I suppose that's appropriate. Um, for me, it was finding out that mathematics really is the underlying language of the universe, and I enjoyed learning mathematics. So learning that mathematics describes what's happening fundamentally in the universe in a very foundational way was very satisfying for me. And once I got into that, I was really hooked. But as you said, there were a few things that don't work right. They seem to be missing pieces. So it also seemed like someone had left a puzzle out on my table, and there it was in my living room every day, waiting to be solved. So this is sort of the approach I take to it. Is every day I try something different with a puzzle a little bit, see if I can get a little bit more of it to fit. And I feel very fortunate to live at a time when everything is not completely solved, but we have enough of it that maybe it can be. So it's a very interesting time. These are, in a sense, very precise questions, but also very abstract ones. And the pursuit of knowledge is nothing if not a chaotic mess. So it's very nice once you know something, it can be cataloged and organized by librarians, and everything seems very well structured. But when you're trying to explore what you don't know, it's a entirely different ballgame. We pull things from all directions. You have things coming from different subject areas that you think wouldn't apply that end up being useful. And it's just a chaotic mess, but it's a very human, creative mess. So it's a very fun process. I find that paradigms and structures are more what gets established after the understanding is already there. So once you understand something, you have to figure out how what you understand fits in with everything else that you understand. And that's where you talk about paradigms as being like an overarching framework for how something works. Now, I think fundamentally there are paradigms that you basically cannot escape. So one might say that mathematics itself is a paradigm for understanding and describing the universe. And one might think, well, let me try to understand and describe the universe with an entirely different paradigm, say through meditation, or through, some people take LSD and just like blow their minds open and try something totally different that's not mathematical. But what we find is that the universe is fundamentally mathematical. So anything you try to do to understand it that isn't mathematics, ultimately, it might be personally satisfying, but it's not going to get you to more practical understanding, if that makes sense. So it's already pretty well established that our universe is mathematical in nature, fundamentally. So although some might consider that a paradigm, I would just consider it a fact, an inescapable fact. So, but there are other things. So um, some might consider, I don't. For me, if I think about, say, string theory, I don't think of that as a paradigm for understanding physics. I think of it more as a toolkit. And then it becomes a question of, is the toolkit worth the effort and study necessary to use the tools? I mean, once you have this fancy toolkit, is it worth the work that it took to get familiar with it in terms of the results it produces? And for many decades, it was promised that yes, definitely worth it. Definitely, this is the answer. This is going to be it. But now it's looking like it isn't. So in that sense, we have a paradigm shift in physics right now. The problem is we don't have really good competitors to string theory for what paradigm to shift to play with. So it's sort of a open field right now, which is happy for me, since I saw string theory as a train wreck happening back in the 90s that I just wanted to get away from and not have anything to do with. And now we're looking at the that developing train wreck, although some people are still in denial about it being a train wreck. So such is the nature of I guess when the train is wrecking, the people in the very front of the train don't always notice what's happening. The amazing thing about science, and the reason it progresses, whereas many things don't progress, many things just go in circles. Not that circles are always bad, is that we make progress by testing things, right? So the reason Einstein's theory of relativity is very successful as a theory of physics compared to Newtonian or classical Newtonian physics is that we've tested it and found it to be true, or at least not yet falsified. And whereas Newtonian physics, we test things and find to be false. And this happened directly as a result, primarily of the development of electromagnetism, which is when we had Newtonian physics where everything is in a sort of a fixed space, and things happen in this space with time, and space and time are very separate things. And in this classical world, when you have something, say someone's traveling along, right? Say they're traveling in a car, say at 60 miles an hour, and they fire a gun, and that gun fires a bullet out of the gun at 1,000 miles an hour. I should use meters per second. You can just guess I'm using meters per second. Then then the bullet is traveling compared to us watching that happen from the outside, it's going 160,000 miles an hour. Or sorry, it's 1,060. The speed of the bullet plus the speed of the car. That's like Newtonian physics, how it usually is understood. But when you write down the Maxwell's equations for the propagation of electromagnetic waves, you have electric waves building up, subsiding, and magnetic waves building and subsiding. And these things travel in a wave. And when you write down the equations for how fast these waves should go, they should all go at the same speed in a vacuum. We call that speed c, the speed of light. It's like 3 times 10 to the 9th meters per second or so, very fast. But it's a fixed speed. So you write down these equations, it's like, okay, well, there's a light beam going by at c. And what happens if you're traveling in a car and you turn on a light bulb and see how fast that light goes in front of you, let's say your headlights? Okay, well, if you're sitting in the car, you see those headlights go at the speed c, right? Just as if you had fired a gun and it goes at 1,000 miles per hour or more. But the people outside the car, they see the headlights, it's going at c, the same speed. How that can't make sense? That's not Newtonian. So the Newtonian description of space and time fails for light. And light is very fundamental. Turns out a lot of things, anything massless in this universe goes at the speed c, not just light. Gravity waves, other forces, anything with zero mass travels at the speed of light. And this told Einstein something very fundamental about space and time. It said that they're linked, and they're not the same for 2 different observers traveling at 2 different speeds. So what happens is the space and time, that you see, if you're watching a car go by, shining its light, you see its speed c, and the person in the car sees that it's speed c. And the reason is you see the car actually contract to be shorter and time to take longer, so that it is in fact c as measured by both. So this was a radical change in our conception of space and time. It's no longer that space is a stage and time is what happens in the universe as it ticks along. It is that space and time itself is a fabric, and that fabric is different based on how fast you're moving through it and in it. And this is a radical reforming of space and time. And then Einstein, again, with thinking about gravity, thought that, okay, well, not only for things moving, but for things accelerating. It turns out that when you feel yourself accelerating like an elevator, right? If you're increasing in speed, right? then you feel yourself, pushed against the floor of the elevator because it's accelerating you. And if you're standing on the surface of the earth, just standing still, you also feel yourself pushing against the floor right now with your feet. Then that's the same feeling. It's the same effective force. So that acceleration actually is interchangeable with the acceleration or the force of gravity. And this also has to do not only with thinking of space and time with respect to how fast something is moving, but thinking of space and time itself as something is curving, right? So that time is moving, I think, more slowly closer to the surface of the earth than it is out in space. And then things follow trajectories that are sort of the straightest possible paths through space and time. And that's why they seem curved, is because the space-time they're traveling through is curved. And this is why we have the force of gravity. Radically different view of gravity than the Newtonian one, where you just have a force from a point mass that attracts other point masses. Very, very different. But it turns out you can measure these differences, and we found Newton to be wrong in this domain and Einstein to be right. Don't get me wrong. What Newton figured out before anybody else was absolutely amazing, but that shifted and it wasn't absolutely correct. Whereas Einstein now we find to have been much more correct in much more domains. Except now, if we try to combine quantum mechanics with Einstein's description of general relativity and talk about something like the physics that happens near a black hole singularity, we find that our description fails. Quantum mechanics itself is much more comfortable in Newtonian or even a special relativistic framework where you have a sort of a fixed background, right? We do quantum mechanics on a fixed background space. But if we try to do quantum mechanics in a curved space-time, they don't play nice together. Like nobody knows how to describe gravity, this curving space-time, quantum mechanically. That the idea for the understanding of how to do that yet is an open question in physics. Nobody knows it. You can ask Google. There will not be a definite answer. There are a bunch of ideas, and none of them really work perfectly well. So we live in a time where we don't understand everything. There's space for a new Einstein to come along and figure out how quantum gravity works. It's one of the most fascinating questions of our time that remains unknown. And the amazing thing is there has to be an answer. The universe works, so we're here in something. There has to be some way in which it's working, and that everything else in the universe we know of that we can describe well as mathematical. So there has to be a mathematical description. We just don't know what it is. So hopefully somebody can find it, or maybe the machines can, since they're likely to be smarter than us soon. This has gone through, the nature of time is fundamental to all of these questions. It was seen by Einstein to be mixed together with space. And that seems like it cannot be disentangled. But in quantum mechanics, time is much more like it is in Newtonian physics, where time is a parameter for how things evolve. And it's not so much coupled with space. Now, when I formulated E8 theory back in 2007, I had the idea that space and time would live together inside what's called the E8 Lie group. And what a Lie group is it's a tangle of geometry. And it's a very pretty tangle that you can describe its structure, and it gets very intricate. But it's a tangle of many dimensions. And what I did in 2007 is see that you could embed 3 dimensions of space and 1 of time in a what's called a de Sitter space-time, which is it's sort of like a 4-dimensional hyperbola, if you like. That you can embed this inside the E8 Lie group, and then let this Lie group deform, and then that would look like curving space-time. So what I did in 2007 is see that this looked very much in line with Einstein's theory of gravity, and that you could have this structure inside this E8 Lie group, which could also contain the other forces known in physics, the weak force and the strong force, as well as electromagnetism, and also gravity. and also that it contained the matter forces. This fundamentally, it contained the structure of electrons and quarks and neutrinos. And there was a hint that would also explain the second and third generation of matter, which we see in particle colliders, which are, for the electron, it also has the muon and the tau as higher mass partners. And there's a whole zoo of elementary particles here, and this E8 Lie structure, which is very pretty, seemed to contain all of it. As I worked further with that, after the initial discovery of how well that fit, as I worked further with it, I saw that time did not actually fit in that well. So at this point, decades later, I have been working to try to figure out how to use this same theory, but extend it to describe quantum mechanics and time in a way that's more consistent with what we know of quantum field theory and how time unfolds that way. And I'm still working on this, but what I find is that the original E8 theory does not work for quantum mechanical time the way it needs to be correct. So in order to find something correct, we have to go beyond the E8 Lie group, probably to infinite dimensional Lie groups, generalized Lie groups, which I can talk about, but it starts to get technical. This depends on which high energy physicist you ask, very much so. So what was found is that in conjunction with the string theory toolkit, one of the tools in the string theory toolkit was the existence of this other symmetry that would potentially exist called supersymmetry. And what the symmetry basically says is that for every force particle, like the weak boson, there's a other partner matter particle. Okay, that's a fermion. That's a massive fermion. And while we don't see this symmetry in nature yet, people thought, well, maybe these supersymmetric particles, these partners to the known particles, were just supermassive, so we hadn't seen them yet. But people would say, well, why would the symmetry exist? Well, it makes the mathematics a little nicer, is one thing, and two is it helps solve a problem with the Higgs boson mass. So if you look at what the mass of the Higgs boson is, in order for it to have the mass it does, you have to have a lot of things in quantum field theory balance. And if you have a lot of, if you have the superpartners to the known particles, you can cancel out terms and get the Higgs particle to have reasonable mass. Another thing is if you look at, people looked at unified theories, where they said, okay, well, maybe at higher energy, if you look down at smaller and smaller, closer in distances, then the weak force, the strong force, and electromagnetism all look like the same force, maybe. Right? They all sort of converge and have the same strength if you use particle colliders and look smaller and smaller distances. And this works better if you have superparticles, right? You can get these three lines to converge a little better if you have superparticles, but they still miss, right? It turns out in order to solve the problem with the mass of the Higgs using superparticles, the superparticles have to have a certain mass, and they should have been seen in the Large Hadron Collider. So at CERN, I visited, and they basically had signs up, on the wall saying, "Welcome home, superparticles, welcome, we'll see you soon." And it didn't happen. Okay, they looked, and no superparticles. So this has theorists pulling their hair out. You can see mine's gone. Because there are no superparticles, as far as we can tell experimentally, and they don't exist where they need to do the electroweak balancing for the Higgs mass. People who really believe in these things still think they're going to be found. So personally, they're not part of E8 theory or these the unification models I work with. So I never thought superparticles would exist. Nice. Thanks, Apple. So I actually made a bet with another physicist, a wonderful fellow named Frank Wilczek, who bet me that superparticles would be seen at the LHC, and they were not seen. So I have a check on my wall from Frank Wilczek for conceding the bet and funding my institute. And on the memo part of the check, it says supersymmetry delayed. You know, not absent, not that it doesn't exist, just it's delayed. It hasn't shown up yet. Right. Yeah, don't hold your breath. So yeah, I don't think supersymmetry exists in nature. Many people still do. It's an open question, and one that we can continue to probe experimentally and continue to make it less and less likely to exist. And hopefully this will motivate people like I have to come up with theories, unlike string theory, that do not need supersymmetry as part of their formulation. Ultimately, it has to solve this problem. So when I was in graduate school and back in the previous century, I was very much in love with Einstein's theory of general relativity and differential geometry and the description of gravity using curving spacetime. And there's this wonderful theory that was formulated shortly after Einstein's proposal that if you added more dimensions, then you could describe not only gravity, but also electromagnetism. If you add more dimensions, you can describe the weak force and the strong force. So just by adding extra dimensions that are also get wrapped up by the laws of general relativity and gravitational curvature, you can have these other dimensions that are attached to spacetime, and they warp around our spacetime in exactly the way you need to describe these other forces. You have to choose a specific shape to get this to work, but you can get it to work. However, when you try to do, if you say you're going to try to do this and also describe electrons or quarks or neutrinos, it doesn't work. Okay, why is that? Well, the gauge fields, which are the force fields of electromagnetism, the weak force, and the strong force. These are specific boson particles that they basically transform like you would expect for a wave that has a direction, like a polarization direction, right? So an electromagnetic wave traveling through space, it has a polarization direction. And say you rotate it. Well, if you rotate it, say you spin it around in a box 360 degrees, it returns to the same direction, just like you would expect. Fermions are different animals. They don't transform like this. If you put an electron in a box, you rotate it the box 360 degrees. The electron is no longer exactly where it started. Now it has a phase change of -1. In order to get it back to where it started, you have to rotate the box 720 degrees. Okay, this doesn't work with this description of adding dimensions to space-time. You can't do it that way. You have to add what's called it's called a spinor field, which is a very different kind of field than a gauge field. So spinor fields, general relativity, they don't match up well. So in graduate school, I was like, well, we have this beautiful theory of general relativity and gravity, and it can explain the other forces. What the heck is up with electrons? Okay, what are electrons geometrically? In quantum field theory, we describe them as a matrix of complex numbers that transforms in this way into rotations. Great, it's consistent, it works, it gives us correct answers and calculations, and we can sort of, in this weird way, glue it into general relativity, but it's definitely something separate. So you have these two things. You have gravity and the forces, and you have the electrons and the matter and the quarks. Now, what I found in 2007 is that they are part of one single Lie group. This E8 Lie group actually has the structure of spinors in it. And that was the main thing I was super excited about when I found that, is that fermions as spinors are described by these exceptional Lie groups. And this is a discovery that's motivated my research ever since. I do think it's something fundamentally important to the universe that exceptional Lie groups have this property. It could explain fundamentally where spinors are coming from, why they exist in nature, if it is in fact, if our world is in fact an excitation of these exceptional groups. but it doesn't work perfectly yet, so it's still getting worked on. It's fundamentally an exceptionally simple theory of everything is fundamentally a pun, okay? But it's an informative pun, okay? Because technically, to have a theory of everything, you have to combine the electromagnetism, the weak force, and the strong force. Once you combine those fundamental forces into one structure, that's called a grand unified theory. And if you combine that also with gravity, technically that's called a theory of everything. Okay, even though you haven't included matter yet, and even though it might not correctly describe quantum field theory. Okay, it's still called a theory of everything technically. Now, what I did is try to get all that algebraic structure together and embed it in a single Lie algebra. Okay, and when you classify Lie algebras, right, you can always combine more Lie algebras to make what's called a non-simple Lie algebra. Okay, but if a Lie algebra is just one consistent structure, right, that is well, it has certain properties that make it just like a simple building block, right? We've classified what all the finite dimensional simple Lie algebras are, and they have to do with things like the symmetry of rotations. Right? So if you try to rotate things in space, right, you have 3 different axes you can rotate things around, right? And that's that Lie group is called SO3. It's a group of rotations in 3 dimensions. Now, if you include space-time, right, then you have those SO3, you have the 3 dimensions that you can rotate in space, but you also have one in time. So when you rotate something in time, that's a velocity in different directions. So that's a 6-dimensional Lie algebra. Right? We call that SO13. Now, these Lie algebras, as well as describing the symmetries of things, they also have themselves this structure that you can describe. So they're mathematical objects in and of themselves that are very pretty. And you can describe their structure with the sort of twists that some dimensions have around other dimensions. And that's called a root diagram. And these root diagrams, for larger and larger Lie groups, get prettier and prettier. Now, as well as the rotations in like real space and complex space and different spaces, among these Lie algebras, you have these 5 exceptional cases. So you have these 5 what are called exceptional Lie groups that stand out from the others. And that's G2, F4, E6, E7, and E8. So E8 is the largest simple exceptional Lie group. So what I did is I found this whole mess of algebra in physics of interacting elementary particles and as a field theory, and embedded that in the E8 Lie algebra. And that's where I got the name. It's an exceptionally simple theory of everything. And since you can describe the structure of E8 using root diagrams that are quite pretty, you can associate the known particle charges with the coordinates of these roots in 8 dimensions, spin them around, and get all the pretty patterns that you would of the charges of particle physics. It's really extraordinarily pretty. So that's the model I came up with in 2007. Turns out it does not completely capture either the flow of time correctly or quantum field theory correctly. So it turns out to describe quantum field theory, like if you imagine physically a laser beam, right? In a laser beam, you can have an arbitrary number of photons in the same state. So it's important in your theory that you have not just one dimension for a type of particle like a photon, but that you have a different dimension for each possible number of photons that could be in a state, if that makes sense. And that's arbitrarily large. So that means you need a Lie algebra with an infinite number of Lie algebra dimensions. And we have, mathematically, they're known. They're not super well studied. They've been studied quite a bit, but not as much as finite dimensional Lie algebras. Excuse me. So that's what I'm working on now, is how to look at generalized Lie algebras in a way that that is compatible with quantum field theory. What you'll find is you have to consider each of these individually. and each one brings different things to the table. String theory itself is a very large, some would say very successful toolkit. Okay, it's a toolkit for describing particles via either strings or other higher dimensional membranes embedded in other higher dimensional manifolds. So string theory is all about embedding one thing inside another and trying to get a description of interactions based on the excitations of one thing inside another. Okay, but there's a huge toolkit for that, and it gets much more general. It goes all over the place. It's a huge structure of tools at this point. But one of the things that's fundamental to it is it does almost always require supersymmetry as for consistency as part of the theory. For geometric unity, what proposed by Eric Einstein, fundamentally, he's building from the ground up, starting from as few assumptions as possible about a metric and the space of metrics. And one of the cool things Eric figured out is that if you try to figure out how to match up fermion fields, like spinor fields, with a geometric theory that involves a metric, then usually when people do this, you have to choose a specific metric. But he chooses to work in geometric unity in the space of metrics. So he's dealing with a theory that has to do with the space of metrics and formulates a theory based on that, and then goes off from there in different directions that also tries to include the Standard Model as best he can. Doesn't work perfectly. He has to tweak a couple of things. His third generation of fermions is a mess. But it's it has some promise to it. For what I work on, I find that I include more of after having built it up from the bottom up, from the Standard Model and gravity up to the algebraic structure, embedding that in an exceptional algebra, then I have to look from the top down. And so my approach to unification is to say, okay, you build up to these theories, and it could be one of these several, and then you take each one of these several and look from the top down and see if it does match the structure we see. Problem is there are a lot of choices for what it could be before you look from the top down. But the idea is that the really motivating idea here is that our universe is just one mathematical object that has come to life, right? So if the idea of exceptional unification is correct, that means our universe is one generalized Lie group that has become excited, and that's it. And you could describe the whole universe that way. If you pick the right Lie group and the right way that symmetry breaking occurs with it, then you should be able to get everything from that. So that's a sense in which it attempts to be simpler than others, but at the cost of that simplicity is restriction. Okay, you're restricted to only whatever result you get after you break the symmetry of some larger Lie group, and then it's more like a giant search for which one might give you our universe. Okay, but they're similar to string theory. There are a bunch of tools here, so there are much of hints, especially from what are called division algebras, right, where you have not only the real numbers but complex numbers and quaternions and octodions, and that's it. But you also have their split versions, which are less well known. But you have a lot of mathematical tools to play with, so it keeps me busy. The best thing you can do is learn and understand general relativity, and learn and understand quantum field theory, and learn and understand the structure of the Standard Model, and try to think about these in a consistent way where you can write down the interactions all on a sheet of paper in the most consistent way possible, and sort of explore that algebraic structure and see what the best way to match that pattern to the breaking of some symmetry of some larger object is. That's the best way to wrap your head around it. So that's a short paragraph of things you need to do, but that requires about maybe 6 years of a study to get there. But yeah, you need to basically I guess the dirty secret of what I'm doing is that it is a very minimal extension of known physics. So the idea of exceptional unification is you take what we know of known physics, you take general relativity, the Standard Model, you put them together algebraically as efficiently as you can, and you see that it's part of something larger, and that's it. It's a whole idea. So it's a very minimal extension of known. It doesn't require strings or fairies or magical other spaces to exist. It's just a minimal extension of what we know, and maybe it's part of something larger. And see how close you can fit it. See what you can start out with that's larger and say break it down to what we know. But anyway, there is to put it mildly, a difference of opinion in the physics community over how to do this, because talk is cheap and colliders are expensive. Okay, so there's a lot of talk that happens because it's cheap. And the talk that happens is this theory is more beautiful, this theory is more elegant. The talk and the experiments that happen are like, nope, didn't see it. This is wrong. So like superparticles, nope, sorry, we built a multi-billion-dollar collider. They're not there. Talk is cheap. It's like, maybe the superparticles are even more massive. That's cheap to say, super cheap, much cheaper than a collider. So I do think these things like philosophical aesthetic appreciation for beauty of a theory, I think that's a good guide. It's also very fulfilling to work on theories that are more aesthetically pleasing this way. It certainly drives a lot of my research. Sabine Hassenfelder would say that no, the universe is not necessarily match our standards of beauty, right? The universe is what it is. Maybe the universe is ugly. Maybe the universe is fundamentally a solid state thing underneath that is manifesting ourselves as these standard model. It's like, oh gosh, no, I hope not. I just really hope not. I don't really want to live in that universe. I'd rather live in a universe that is fundamentally the excitations of a beautiful mathematical object. And I'd rather spend my time looking for that. So, every human has their own personal biases. Those are mine. But is it useful? It's proven useful in the past. So Maxwell's equations, before Maxwell, right? When we didn't know, when we didn't think about time-varying magnetic fields, right? We had maybe time-varying electric fields and we had magnetic fields, but there was an imbalance in the equations. It was just kind of a mess. But Maxwell came along and said, okay, well, what about if we added, part of this equations with a time-varying magnetic field, and then it's more symmetric between electromagnetic, and these things can actually propagate. And look, we get light. That was freaking amazing, and very successful. And that was, that's an aesthetic balancing of equations. One might say the same thing has happened with grand unified theories, right? It does look like the fundamental forces are all part of one larger Lie group, right? This happened long before I was born, where is well, actually no, 50s, 60s, yeah, it's about concurrent. Where people thought, okay, well, these forces all look like they could be part of one larger force. So this is a powerful powerful idea, this idea of unification, and it's basically an aesthetic choice of simpler things are more beautiful. So, but our universe requires not just simplicity. It's not just like, oh, our universe is a sphere. No, it's like our universe is this complexly beautiful but simple thing. So these are aesthetic guides that help to formulate our theories. Like I said, Sabine Hassenfelder would say, yep, no, the universe might just not conform to our ideals of beauty. I mean, and these things are all just misleading us. I disagree. I think it's very important what she's saying. I think it's important to consider. But I go entirely opposite for what drives me and what looks for. I very much use beautiful mathematics as a guide to what I think is true. But experiments, I also think that Sean Carroll has been put in a funny position in saying that it's up to us as a community of physicists to decide what's true and what isn't, because colliders are too expensive. I disagree. Okay, I do think that empiricism ultimately is the guide, regardless of what the community considers to be a good theory. I think empiricism ultimately is our guide, and we can't just cast aside hundreds of years of scientific progress because it's hard or expensive. Okay, I do think that just give me another collider, man. Just a little bigger. Just give me a little bit bigger. I know it's some money, you know, but just a bigger collider will figure a lot more stuff out. Yes, please do that. I was heartbroken when the superconducting super collider was canceled. Probably would have learned a lot from it, other than how to dig holes in the Texas desert. But yeah, it's hard to imagine a more it's hard to imagine a better goal to aspire to than to figure out the ultimate rules and laws of this universe. I was recently watching an interview with Sam Altman, who is CEO of OpenAI, working on artificially intelligent models. And he was asked, like, what would, you know, if you do get a model that has superhuman intelligence, right? That, you know, you have a lot of resources here and you finally succeeded in building a super intelligent AI. What do you ask it? And he didn't ask, like, well, how do you solve the climate crisis, or how do you, you know, find peace for humanity? Which are all, you know, wonderful questions to ask. It's like the thing that popped into his head to ask it is like, what are the ultimate laws of the universe? Right? There's no grander puzzle to be solved, I think, than that one. And I think that not only is that the grandest problem I think we can aspire to solve as humans, I think it is the grandest problem that superhumans will be able to aspire to solve. So hopefully that's the future, not only of humanity, but of our progeny. I'm coming towards what I would laughingly refer to as my scientific career. I'm coming towards the end of it. And I'm seeing my competition not as other physicists, but as intelligent machines. I think, I don't know if you followed the progress of like machines learning to play Go against humans, but reading about it, the skill level of algorithmic Go players versus the best humans, right? It's like it went for a long time. Machines weren't very good, and you could just easily beat a Go algorithm playing Go, and then suddenly they matched the skill of the best players. And looking and reading about it, and that was from studying human games, right? So these algorithms were trained on human versus human Go games, and then the algorithms started being trained just on playing themselves, right? More just massive amounts of computational power in a quarter playing Go with itself. And they got to be amazingly good playing themselves. And from what I read, the window of time during which the best computers Go algorithm were matched with the best human players was about 20 minutes. Okay, so they were a lot stupider than us. Then they got pretty good. Then they got better. Then they were the best human players for about 20 minutes, and then they were much better, and they just wiped the floor with the humans. Okay, so that's the window. It's not like human intelligence is some, you know, peak at which all intelligence will plateau. I think machine intelligence is coming. We're down here, and we're coming like this. And it's like, oh, that's pretty good. That's pretty good. Oh, that writes better than me. Oh, that takes the LSAT better than me. Oh, yeah, that takes the math Olympiad better than anyone. Oh, yeah. Oh, yeah. Okay. Well, we're working for them now. I think it's just going to go blow past human intelligence. And when that happens, I'm out of my career's done. Right? That is the window at which I can no longer make progress faster than the machines can. I just hope they'll be nice to us and let us live in nice nature preserves and tell us what the laws of the universe are and the way we can understand at that point. And I'll spend more time surfing. Who knows? If things go really well, maybe I'll live even a whole lot longer or augment my own intelligence. But with your question of what advice to give to young people is get on the winning side. You don't want to go study string theory right now. It's dying. String theory is dying, right? It's old people talking about, oh yeah, this is still the best game in town, right? This is very successful theory. No, man, string theory is dying. If you're a young person right now, you're not going into string theory. Go study machine learning. Go work on the algorithms that will supersede human intelligence. You'll get rich. You'll have much more happiness. You'll see much more progress in your field. If you want to still study physics just as a way of understanding and appreciating it and maybe make progress in it and then like get help from the machines with how to move it along, do that. Great, fantastic. But machine learning is where the future is for young people. You know, move that along, be part of that wild adventure. Certainly don't go into strings. If you want to talk to me about helping me with E8 theory, possibly using machines or possibly using your own impressive brains, that's fine. I'm always happy for outside help. But yeah, that's basically my advice for young people. And I'm probably not the only one saying that.